Let's delve into the fundamental concepts that underpin electrical systems. Understanding these principles is crucial for anyone working with or studying electricity. We'll cover key aspects, breaking them down into easily digestible segments. Firstly, consider voltage, often described as electrical potential difference. Voltage, measured in volts, is the driving force that pushes electric charge in the form of current through a circuit. Think of it like the pressure in a water pipe. The higher the voltage, the greater the pressure pushing the electrons. Secondly, there's current, measured in amps. Current represents the rate of flow of electric charge. It's the quantity of electrons passing a given point in a circuit per unit of time. A higher current indicates a greater number of electrons flowing. Thirdly, resistance, measured in ohms, opposes the flow of current. It's the property of a material that hinders the movement of electrons. A higher resistance means it's harder for current to flow. These three quantities are related by Ohm's law, a fundamental relationship in electrical circuits. Ohm's law states that voltage equals current multiplied by resistance, often written as voltage equals current times resistance. This simple equation is a cornerstone of electrical circuit analysis. Rearranging Ohm's law, we can also find that current equals voltage divided by resistance, or resistance equals voltage divided by current. Now, let's consider power, measured in watts. Electrical power is the rate at which electrical energy is transferred or consumed. It is calculated as the product of voltage and current, expressed as power equals voltage times current. A higher power rating indicates a greater rate of energy consumption. Energy, measured in joules or kilowatt-hours, is the capacity to do work. Electrical energy is what powers our devices and appliances. Kilowatt-hours are commonly used to measure energy consumption by households and businesses. Understanding the difference between direct current and alternating current is also essential. Direct current, or DC, flows in one direction only, from the positive terminal to the negative terminal. Batteries and electronic devices typically use direct current. Alternating current, or AC, periodically reverses direction. The frequency of this reversal is measured in hertz, with 60 Hz being the standard in many countries. AC is used for power distribution because it can be efficiently transmitted over long distances using transformers. Transformers are devices that increase or decrease voltage levels in AC circuits. They work on the principle of electromagnetic induction, where a changing magnetic field induces a voltage in a nearby coil. Step-up transformers increase voltage, while step-down transformers decrease voltage. This ability to easily change voltage levels makes AC ideal for power grids. Electrical circuits can be classified as series circuits or parallel circuits. In a series circuit, components are connected one after the other, so the same current flows through each component. The total resistance in a series circuit is the sum of the individual resistances. If one component in a series circuit fails, the entire circuit is broken. In a parallel circuit, components are connected side by side, providing multiple paths for current to flow. The voltage across each component in a parallel circuit is the same. The total resistance in a parallel circuit is less than the smallest individual resistance. If one component in a parallel circuit fails, the other components continue to function. Electrical safety is of paramount importance. Working with electricity can be dangerous if proper precautions are not taken. Always to energize circuits before working on them, and use appropriate personal protective equipment, such as insulated gloves and eye protection. Grounding is a crucial safety measure that provides a low resistance path for fault current to flow back to the source. This helps to prevent electrical shock and equipment damage. Circuit breakers and fuses are overcurrent protection devices that interrupt the flow of current when it exceeds a safe level. Circuit breakers can be reset while fuses must be replaced. Understanding the National Electrical Code, or NEC, is essential for safe electrical installations. The NEC provides guidelines and standards for electrical wiring, equipment, and systems. It covers a wide range of topics including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is updated every 3 years to reflect changes in technology and best practices. Some key NEC articles include Article 210, which covers branch circuits, Article 250, which covers grounding and bonding, Article 300, which covers wiring methods, and Article 310, which covers conductors for general wiring. These articles provide detailed requirements for electrical installations. For example, NEC Table 310.16 provides ampacity ratings for conductors based on their size and insulation type. Ampacity is the maximum current a conductor can carry without exceeding its temperature rating. Selecting the correct conductor size is crucial for preventing overheating and fire hazards. Voltage drop is another important consideration in electrical circuit design. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, use larger conductors or shorten the circuit length. Understanding electrical diagrams is essential for troubleshooting and maintaining electrical systems. Single-line diagrams provide a simplified representation of an electrical system, showing the major components and their connections. Schematic diagrams show the detailed connections between components, including all wires and terminals. Ladder diagrams are commonly used for control circuits, showing the sequence of operations. Electrical meters are used to measure voltage, current, resistance, and other electrical parameters. Multimeters are versatile tools that can measure multiple quantities. Clamp-on ammeters measure current without breaking the circuit. Insulation testers, also known as megameters, measure the resistance of insulation to detect faults. Power quality analyzers measure voltage and current waveforms to identify disturbances and harmonics. Harmonics are unwanted frequencies that can distort voltage and current waveforms, causing equipment to overheat and malfunction. Power factor is a measure of how efficiently electrical power is being used. A low power factor indicates that a significant portion of the current is not contributing to useful work. Power factor correction can improve the efficiency of electrical systems by reducing losses and improving voltage regulation. The electrical grounding ensures a safe path for fault currents, minimizing the risk of electrical shock and equipment damage. Grounding electrodes, such as ground rods or ground plates, are used to connect the electrical system to the earth. Bonding is the process of connecting metallic parts together to create a low-impedance path for fault current. Ground fault circuit interrupters, or GFCIs, are devices that protect against electrical shock by detecting small leakage currents. GFCIs are required in wet locations, such as bathrooms and kitchens. Arc fault circuit interrupters, or RFCIs, are devices that protect against electrical fires by detecting arc faults, which are dangerous electrical discharges. RFCIs are required in bedrooms and other living areas. Surge protection devices, or SPDs, protect against voltage surges caused by lightning or other transient events. SPD divert the surge current to ground, preventing damage to electrical equipment. Electrical maintenance is essential for ensuring the reliability and safety of electrical systems. Regular inspections should be performed to identify potential problems. Thermography, using infrared cameras, can detect hotspots in electrical equipment, indicating loose connections or overloaded circuits. Insulation resistance testing can detect degradation of insulation, preventing electrical breakdowns. Tightening connections and cleaning equipment can improve performance and extend the lifespan of electrical systems. Finally, understanding the principles of renewable energy sources, such as solar and wind power, is becoming increasingly important. Solar photovoltaic, or PV, systems convert sunlight directly into electricity using solar cells. Wind turbines convert wind energy into electricity using rotating blades. These renewable energy sources can help reduce reliance on fossil fuels and mitigate climate change. In conclusion, understanding electrical systems involves mastering fundamental concepts, safety practices, and practical applications. By grasping the principles of voltage, current, resistance, power, and energy, as well as safety measures like grounding and overcurrent protection, individuals can confidently work with electricity and contribute to a safer and more efficient electrical world.